Thanks, Fred. Thank you guys for coming. Really appreciate it. So as Fred says, I'm going to talk about Anycast. But before I dive into the detail, I just want to give you a bit of background on our journey to what has enabled us to capitalize on it as much as we have. I spoke here last year about changes in the world of networking and this trend away from big fridges, as I called them, controlled by a handful of vendors, towards merchant silicon, mass-produced, super high performance but low cost silicon that can forward packets in hardware, but with great software control, and the software side of it starting to open up. And this world of networking that had previously been closed, coming to the standards that we expect in the world of voice, namely the ability to abstract signaling and media and control them both in separate planes. I'm taking it a stage further today. At the time, we were going through the process of replacing our legacy Brocade network stack with a flat stack of merchant silicon based on the Arista platform, and that's enabled us to fast forward quite a few other things. Also, since last year, and for those that don't know us, actually, we're historically a UK-based termination origination operator. We operate our own IP and SS7 network in the UK, including fibre in the ground in certain places. But our largest customer is actually US parented, so having serviced them for the rest of the world, they were quite insistent that we put ourselves in a position to do US local. So as of this year, we've got East and West Coast POPs. We're now a US C-LEK. We're going through the whole process with MPAC registration, et cetera, et cetera. So that has required certain changes in the way that we do things. Another change has been around containerization. Historically, we used to be bare metal for anything that was handling media, and virtual machines on bare metal for anything that was signaling or app-based, basically anything that wasn't handling media. We brought all that together in containerization, leveraging Docker, but it's been an interesting journey because that's quite a mysterious world. And when we first peeped into it, there was one thing that stood out that was a massive blocker for us, and that's this freaking Docker proxy thing, as they call it. Those that don't know it essentially NATs from the outside to inside, and it also bridges between containers. So with my network engineer hat on, bridging inside a host feels fairly yucky. With my SIP hat on, NAT feels even worse. That just wasn't going to work for us. It'd be fine for APIs, for web apps, but it wasn't going to work for us for SIP usage. We needed to get to a position where a container could be a first-class citizen on the network, the same way as a VM used to be, the same way as bare metal used to be. And we went through a few iterations of this. The first way was probably the most elegant on paper, but the least practical in operation. That was essentially replacing the Docker bridge with our own plugin to Docker. The second way, frankly, works and is operationally far cleaner. And that is, within each container, we run a tiny BGP daemon. On the host, we run a tiny BGP daemon. So we instantiate a container. It announces to the host, hey, I'm here, I'm this IP address. And the host announces that out to the network, makes it work. Traffic is routed all the way to the container. So the container is that full first-class citizen on the network with an external IP address. The project that really made a difference to us there was GoBGP. Originally, we were running Quagga on the host alongside our plugin that replaced the Docker bridge. Quagga is the go-to product for this, but it's a beast. You'd be nuts to try and run that inside a container, particularly if you've got lots and lots of microservice-style containers. GoBGP, on the other hand, is super lightweight, super fast, written in Go as the name suggests. The other interesting thing with GoBGP is there's a couple of modes you can operate it in. You can operate it as a daemon with flat file configuration, or you can operate it as a library for your own code, which creates some quite interesting opportunities in terms of conditional announcements to the network, things like that. So where we ended up after this was we got rid of this Docker voodoo. There was no user LAN proxy. There was no NAT. Other than for applications where we wanted it, we still had the capability to do it. We'd built in the fact that the container could announce its presence to the network, so the devs building container images are in control of IP addressing, that side of things, but they're also in control of security through a side project to GoBGP called GoPlane. Now, GoPlane leverages a technology called FlowSpec. FlowSpec enables you to carry essentially firewall rules in BGP. So our container, when it spins up, says to the host and in turn the onward network, not only, hey, I'm here, this is my IP address, but it also says, right, I want these ports from these sources in these protocols. And because it's carried over BGP, it's ephemeral. So wherever that container is deployed, those firewall rules are deployed. When that container is removed, those firewall rules go away again. And operationally, that's made a huge difference because our devs are now doing the job of previously 3 people. There's no network engineering involved. There's no security involved. They're in control of the whole pipeline. But the biggest benefit from all of this is this thing we call routing on the host. The fact that the host is now a router and traffic is routed all the way to the container. There's no layer 2 complexity. We've got a very flat layer 3 architecture. And the benefit from routing, or one of the benefits from routing on the host, is this thing we call Anycast. Now, at the risk of offending a few people in the room, I want to go back to basics and make sure we're all absolutely clear what Anycast is, because it's one of those words that sounds kind of cool. Sounds kind of big, sounds kind of global. So the marketing people love it. So there's several people that have Anycast that don't. So let's be clear how the internet works and what it is. So the internet is the interconnection of multiple networks. A network might be Google, it might be your access provider, it might be Simwood. A network is also referred to as an autonomous system. An autonomous system is given a number called an autonomous system number, ASN. So Simwood is AS42353. And those ASs interconnect with each other, indirectly, directly. And there may be multiple connections between any one AS and any other. If I look at our network, we're directly interconnected with something like 600 other ASs. They could be customers that are directly interconnected and are ASs themselves. They could be peers through an IX or directly, or they could be transit providers. That isn't Anycast. That is multi-homing, and that's essentially how ISPs work. The opposite of that is single homing, which is a bit like you at home with your DSL connection. You're connected to a single provider. An AS is authoritative for a block of IP addresses or several blocks of IP addresses called a prefix. So that prefix, in theory, exists only once on the internet behind that one AS, even though there may be other ASs that enable traffic to get there. It sits behind that one AS. Within that AS, it likely sits on one server or one leased line or one load balancer. That is unicast and how the majority of services that we use every day work. Anycast is very subtly different in that address, rather than sitting on one host, can sit on 2, can sit on 3, can sit on 100,000. So within that AS, when it has traffic targeting a particular IP address, it has multiple choices of how to get it there. And they all have different costs, and routing protocols will pick the lowest cost route to that IP address. We've all used this. In fact, we use it quite heavily day to day without knowing it. Those are the Google DNS servers that you're probably familiar with. You go to Australia, ping them, they'll be very close. You go to LA, ping them, they'll be very close. The reason? Because they're everywhere, and because they're Anycasted, and because the way Anycast works, your traffic will be routed to the lowest cost instance of that IP address, which is normally the one that is closest to you. DNS is the perfect poster child, if you like, for Anycast. And some years ago, people thought it was pretty much the only service you could run on Anycast because there's a big problem with it. You are routed to the closest instance of that IP address, but if we're talking about doing that across the internet, say from here to the Google DNS servers, any one ISP along the way could have a change in their network topology. They could have a router go down, JCB go through a fiber, what have you. So the best route to that IP address could change midway through you using it. So you're talking to a server over here 1 minute, and then you're talking to a server over there the next minute. It doesn't affect DNS, because DNS is simple question, answer. It doesn't matter that your next question and answer goes over there. If you've got a long-running TCP session, say, going on over here, and all of a sudden it swings over there, you've effectively been disconnected and got to reconnect. But the content delivery networks a few years ago thought, well, hang on, we can probably use this for HTTP. And you might think, well, HTTP is TCP, potentially relatively long-running compared to DNS. Is it going to work? Well, the answer is yes, it does. Most content-delivered network, CDN stuff that you know, downloading music, iTunes, that type of thing, is delivered over Anycast now. And there's been a number of statistical analyses as to how much this route flapping on the internet actually affects the user experience. And it's minuscule. I can't remember the exact figure, but it's of the order of less than 1%, significantly less than 1%. But there's still a difference. If you're downloading a web page, say, with 200 objects, the fact that one of those objects may be unavailable because the session has reset isn't a big deal. Worst case, you reload the page. And it's still probably only 20, 30 milliseconds of connected time. That's very different to a 3-hour conference call, which is the world that we work in. But I think Anycast can still help us there. But before we dive into that, just to recap on what it gives us as a benefit. So because these instances are everywhere, and people are everywhere, you get this sort of natural load balancing. So think of the Google example. All of their Australian users hit the Australian node. All of their US users hit various nodes in the US. You also get redundancy, because if a node drops off, yes, the connection, the TCP session, drops, but when it's reinitiated, it will go to the lowest cost instance of that IP address, which will be the next closest node. And the implication of both of those two is that you get this locality. Now, it isn't exactly a geographic locality, it's in terms of network cost, but it's as good as a geographic locality. In fact, the more of these things you have, the more nodes about the planet you have, the closer it becomes to geographic locality. But it's easy to think of Anycast as global and big and sexy. For us, most of the benefits we've derived from Anycast are internal, and I would argue that the closer to home and the closer to the core of your application you go with it, the bigger the benefit you're going to see, and I hope to show that as we move on. So, obvious use case, similar to DNS, is a stateless proxy. Let's say a redirect server. Have them all over the world, same IP address, question, answer. The answer just happens to be a 302 redirect to a unicast proxy sitting in that appropriate particular site. If we take example of a nomadic user, just to ram home some of the points I made a while ago, cruising around Asia, they've got a fixed host name in their SIP client that maps to a fixed IP address that happens to be Anycast. They're going to connect to the Tokyo node. That node dies, they're going to see, if they had a TCP connection, they're going to see that drop. They're going to reconnect to that IP address. The next closest instance of that IP address is going to be London. They have noticed no downtime. They may have noticed the TCP connection drop. They've not had to reconfigure an IP address. They've not had to change the host name. We've not had to change the host name. Nothing has actually changed. And we've lost the entire data center, which I think is pretty cool. But bringing it closer to home, if I look at our network, there's lots of sites there, but fundamentally in the UK, we operate 3 availability zones. And each availability zone has our full application stack in. The idea being we can lose one or more availability zones. As long as we've got one left, we can continue servicing customers. The problem comes when you introduce customers to that, because you can give them a lovely interop document saying send your traffic here, which they will, being engineers, improve upon. So you can very easily get into a situation where rather than using the host name you control, people insist on using an IP address. Rather than using the IP address that you've asked them to use because it's the relevant one for them, they use the IP address somewhere else because they think, hey, it'll be quieter so my calls will connect quicker, or some other logic. But the consequence of that is you could have a customer connected in London forcing their traffic to go to, say, Manchester. So out of our 3 availability zones, they've exposed themselves to an issue in any 2. So if they're sending traffic to Manchester via London, we have an issue in London, they're affected. We have an issue in Manchester, they're affected. With the Anycast approach, and we haven't deployed this yet for reasons I'll say later, but let's say we had a single IP address for the whole network and said to all customers, send your traffic there. Maybe we have a host name mapped to it as well. Yeah, they can override the host name, put the IP address in, but the point is that IP address is the same everywhere. They're going to hit the node that is the first node they come across when they land on the network. So if they're connected in London, they're going to be serviced in London. If they're connected in Manchester, they're going to be serviced in Manchester. And they're only exposed to a single availability zone. But we can use Anycast for stateful services as well, and I think you'd be surprised how far we can go, and indeed we've gone with this. There's a little, when you're working on your own network, there's a little quirk, stroke feature, stroke directive that you can configure in your routers and your switches that makes the experience substantially better. If we look at the typical scenario where we have an IP address anycasted on those 4 hosts at the bottom, each router, each switch along the way will have multiple choices of the way to get to that IP address, and they'll each pick the best one. But the consequence will be that broadly 25% of the packets will go to each host. Now that's fine for something that's completely stateless, question answer. It's useless for something that is remotely stateful, even TCP, because 75% of your packets aren't going to arrive because they're going to go to another host. But there's a really cool feature called ECMP. ECMP stands for Equal Cost Multipath. And if you turn this on your routers, what it says is, for all traffic coming through to a given route, I want you to hash it. And then any subsequent traffic that matches that hash, I want you to send to the same place. So you've effectively got sticky load balancing on your network. So with that architecture that I showed you before, you can ensure that all TCP sessions go to the same host. The hash is by default usually source and destination IP, source and destination port, but you can override it depending on your vendor equipment and make it more specific than that if you want to. Now, when we talk about stateful services, the big thing we've got to define is state, because at one extreme it can mean it's a TCP session. At the other extreme, we can mean it's something like a web session with like a user profile behind it, and they all have different levels of implications as to how we may anycast them. They can all be anycasted, but you've got to be aware of the consequences. At the top, it's very simple. We don't care which node things go to. At the bottom, we want to make sure that everything goes to a specific node, and we've got things to do if that isn't the case. So in terms of your journey with this, you want to start at the top and exercise more control and caution as you go further down. But I'm going to run through each of those and give you some examples. So node agnostic, we don't care which node a given user hits. And we don't care if they get disconnected and they hit another one. We do care that any TCP session they have remains with the same node, but ECMP does that for us. And the great example of that, and we use this massively within Symwood, is read databases, in particular Redis. So Redis is master-slave, as you probably know. We wouldn't anycast the master because we're just going to end up with data all over the place. It's going to be a hell of a mess. But we can anycast the slaves. And by doing so, we can ensure that every read goes to the closest node, and there's multiple alternatives if it fails. Now, you could do writes, to an Anycasted database if you were using a database that supported read and write anywhere, where your client interfaces were Anycasted and then you had a unicast interface for the actual cluster side of it, something like Galera. And then, of course, web apps, which, again, we've done massively within our network. So publicly, our portal and our API are Anycasted, but internally, pretty much every service from the point a SIP call lands on the network is Anycasted within the stack. Give an example. So we've got a host with 2 containers. A call lands on Gamma Elio. It needs to interrogate Redis for call routing information, say. Redis is Anycasted, as is actually Gamma Elio, but Redis is Anycasted, so the closest or the lowest cost route to that Anycasted Redis IP address is going to be the one on the same host. So each Gamma Elio is going to connect to its local Redis. I should point out that each Gamma Elio instance and each Redis instance is completely identical. They're containers, they're fixed images, it's Anycasted, so even the IP address is the same. There's nothing different about those containers on either host. There's no host-specific config, there's no site-specific config. They're just an image pushed to a container. If Redis dies, which it doesn't, but if it did on one of those hosts, our Gamma Elio is going to see that TCP connection drop, and it's going to try and reconnect. But the next closest instance of that IP address, that same IP address, is the host next door. You don't have to worry that it might be a host on the other side of the planet and all of a sudden everything's going to grind to a halt because you've got this massive latency, because your routing protocols are taking care of making sure that you hit the next lowest cost instance of that IP address, which is likely to be the one next door, or at least in the same data center. This also makes things really, really easy from a service discovery point of view. If you take a simple example, web app database, and you want 1,000 instances of your web app and you want 1,000 instances of your database. You've got 2,000 IP addresses to manage, and you've got 1,000 times 1,000 pairings, plus times another 1,000 if you want a backup DB for each web app to manage in terms of your service discovery and deployment. You Anycast it, you've got 2. One for the web app, one for the DB. Job done, easy. The next level of state is where we want sticky TCP sessions, and we don't really mind if a node drops and our sessions reinitiate on another node, but there may be something in the application to take care of when that happens. So an example of that is like a SIP registrar. So people are registering to Gamma Elio over here, that dies, their next registration goes over here. In your application, you may want to be handling either supporting 2 registrations or removing the stale ones. Similarly, voicemail service. I don't know how people architect it generally, but I'd imagine you're sending a specific realm to a specific box or specific users to specific places. You could conceivably have a bank of 1,000 asterisk instances all recording to disk. If you lose one, there'll be some cleaning up in terms of making sure those files are recovered, etc. But in theory, Anycast, they can be the same image deployed everywhere. RTP proxy, RTP engine, with an Anycasted instance, Anycast will take care of ensuring that the UDP streams stop going to that box which has died and start going to that box which is the next closest instance of that IP address. But it needs to know what to do with it. So you need to be managing state behind the scenes to make sure it knows what ports to open, et cetera, et cetera, et cetera. So Anycast is doing the same thing that it was doing in the node agnostic environment, but there's more awareness required in the application. And to take that to a higher level, we call H-Anycast. So we're using Anycast to give HA. And this is a scenario where we want exactly one instance, all traffic going to the same place. Think of a conference call server. But we want it Anycasted, so we've got HA and we've got failover. Now you may be saying, well, I can do this anyway with Keep Alive D and various other things, but they require layer 2 connectivity between the 2 instances, which, unless you're nuts, means they're fairly close together. One dies, The other assumes the IP address, gratuitous ARP, and away you go. If you do it with Anycast, you can do it globally. There's no layer 2 voodoo required. But in either scenario, you need to resume state within your application. I don't think Asterisk has an equivalent, but in FreeSwitch you can write call state to a database, and then on another instance, which Anycast has made available, you can just do Sophia recover, and it will load the call database back in, and away you go. This works perfectly for that. So simple scenario I showed you before, our nomadic user connecting to their closest node. With Anycast, in this scenario, we've got 3 nodes around the planet, but we're leveraging routing protocols to make sure that whilst every one of those nodes has the same IP address and every one of those nodes is active, we're forcing all traffic to go to one of those nodes. But if that node dies, the network in a second or two will deliver new traffic to the next node. And again, if that dies, it will deliver traffic to the third node. So you've got the same kind of failover as you get with Keep Alive D, but at global scale with as many levels of failover as you want. So I don't know how I've done for time, but that brings me to the end. It's pretty powerful stuff. My advice to you would be to have a play with it, but my advice would also be start close to home, start small, start in a data center, start with a couple of servers, couple of services, and build out from there. Because in our experience, all of the wins are here, all of the pain is here. So if you start here because it's something your marketing people can get excited about, then you're going to have problems. You start here, you're going to really see some wins from it. But I'd love any questions if anybody's got any.
Thank you so much. I'm going to give you the mic just so that the questions can go up on the videos and everything. First question.
Thank you. How universal is support for Anycast among the world's ISPs, especially residential ISPs?
Universal, 100%, because Anycast isn't something that they have to support. They're just routing packets exactly the same way as they ordinarily would. They don't know that when you send traffic to 88888, that could be a unicast address. Your ISP doesn't know, none of the protocols need to know. It's only different in the sense that there's multiple paths to it, and the routers along the way pick the best one to it, which they would do ordinarily anyway. So it's completely identical.
Our next question's in the back of the room.
Thank you. You mentioned that you had some reasons that you hadn't fully implemented and that you'd get into that later. What have been your stumbling blocks, and what are your thoughts on resolving them?
This is the globally deployed Anycast proxy. Yeah. Really, that thing that I said about the value being here, we've had such a lot going on in terms of network expansion, complete new stack with containerization that encompasses Anycast. Frankly, we've got so much in the way of new betas for customers to digest and then us to put live. It's a little way down the list to say, hey, here's a new global proxy. The other issue is user agent support for it, because there's two ways of us doing it. One is 302 redirect. So they hit the Anycast proxy, we 302 redirect to the closest unicast actual proxy. So then we don't need to worry about paths changing after that point. But not all UAs support 302 redirect and don't all partially support it. The other way of doing it is receive traffic on an Anycast address, respond from a unicast address, which technically the RFCs permit, but again, user agent support may not be as we want it. So we need to digest some of the other changes that we've got out there, get stuff live as opposed to beta, and then we can put that out as a new beta for customers to play with.
We've got good time for questions. There was one right in front here.
Thank you. If you send a call to a unicast proxy, and this call is sent to a gateway, how the gateway knows which proxy sent the call? If you have at least 3 proxies with the same IP address. Then you send to a gateway. How the gateway knows
You say with a
how
with
to
a
send back?
yeah, you
the
say with
packets.
with a unicast proxy.
Yeah, with the
You mean
proxy.
an Anycast one?
Anycast,
Yeah.
Anycast proxy.
Yeah. So you're absolutely right. When it replies, it will send it to the closest instance of that IP address, which may not be the one that sent it. So you can have some peculiar things going on internally. The way around that, unless that's desired behavior, because that is desired behavior in some instances, and I'll give you an example in a second. The way around that, and this is a good one for the clustered DBs that I mentioned, is Anycast on the client side, unicast on the internal side, and then you don't have a problem. Sorry, but I said...
But you need to have a back-to-back user agent for this. You have to change the address from Anycast to unicast.
No.
No?
No. No, you can have Fred will tell you more about this, but you can have a Camellia with two IP addresses. You just originate the internal request from the unicast one. Where this is desirable, though, is let's say you want to send options pings to all of your customers and discover the closest node to them, say. You can have one server sitting in one place with originating those requests from an Anycast address, and then you can receive those around the network on other instances of that Anycast address and basically see where the traffic comes in.
I think you may have partially answered it, but how would you handle graceful failover with Anycast? So say you have a few sessions to an Anycast node, and then you want to do a maintenance or something, so you want to keep existing sessions, existing flows, and you want to refuse others, and you want other flows that you refuse to fail back to another server. But it's Anycast, so it's IP level, so it will still try again that same server.
Okay. So yeah, you're right. You could withdraw the root and leave the container up, but then that's going to interrupt all of your existing sessions. There's no sort of restart graceful in IP routing, but you do that in your application. I can't remember what the directive is in Asterisk, but on FreeSwitch, for example, you've got restart gracefully, so it will just reject at the application level any new attempts.
But yeah, then it will try again, and they hit, so you have to remove the route, right?
It depends where they're trying again from. So, if you've got a Camellia dispatching across them, depending how you configure that as to whether it tries that same node again or whether it fails over to another one. Yeah.
All right. This side of the room needs to pick it up.
You may have partly answered my question with the redirect server, but I was wondering, you've got multiple high availability zones. Are you not at the whims of where the ISPs decide to peer? So if they all decide to peer in London, then basically all of your traffic just gets pulled to London.
Yeah. So how I said this is where your problems are?
Yeah.
This is where the wins are. This is on your own network. This is on everybody else's network. Now, yes, we see most traffic in London. We see something like 85% of our traffic comes from people that we're directly connected to. But we also have alternative routes to them in other sites. So that just affects the scaling of availability zones and how much headroom needs to be in other sites. Where it's more of an issue is the traffic that isn't coming from your peers. So in our case, it's unusually small because we're so heavily peered. But it's about 15% of our traffic is coming over the tier ones, the original typical transit providers. They frankly do what they want with your routes, and they tend to, one provider in particular tends to have a habit of getting into bun fights with other providers, and you can find that your prefix is announced in London to that provider, maybe drawing in traffic from New York because that's where they've got other customers connected, and they insist on keeping the traffic on net rather than sending it to one of their competitors. So you get peculiar effects like that, which are more of a problem. You can get around them, but it's this. You need to understand what's
the
going on.
onus on you to become a strong peer. Then does it? You're peering wherever you can to try and get the traffic as close to you as you can.
Yeah. So we peer everywhere. We're at an IX in every single site that we've got. We also encourage customers to connect directly and to do so as many times as makes sense with their topology. Because the reality is, if they're connecting in a single site and that site dies, then either they're not connected to us at all, or they're falling back to transit or something else.
Start thinking of one.
It seems that a lot of the problems that people are raising with failover gracefully and things like that are easily handled by doing a redirect server at the SIP registrar level. Is that correct?
They're handled by thinking about what you want the Anycast to do, yeah. So if the closer to stateless you are, the fewer problems you'll have with that. The closer to stateful, with only one place for it to go, the more problems you'll have. And that's that slide I had where showed complexity and problems at the bottom end. But yes, you can go very deep with this from an Anycast point of view, and we have, but you need to do so consciously. But you don't need to think of Anycast as a global thing. You can do Anycast within a data center. And then what the rest of the world does with those IP addresses doesn't affect you. And we do this. So we have certain services that have a distinct IP address per site, but that IP address is Anycasted within that site. So we can force traffic to the appropriate site by the choice of IP address, but when it's there on our network with ECMP, with us controlling topology, it's a nice place to be, and we don't need to be stateless, because the reality is if the topology changes within one of our data centers, then that's generally a failure scenario that you'd want the topology to change for anyway.
Still on the same side of the room, 1 second.
What is your thoughts on recovery strategies? I mean, I've seen people playing with registration timeouts, qualifies, all of it adds network load. And one of the alternatives would be switching to TCP. In this type of scenario, the closing of the TCP socket would trigger the user agent to re-register with lower traffic. But are there any pitfalls to that?
Again, that's probably a question that somebody asked Fred, to be honest. Somebody more expert in Camellia than me would probably be a better person to answer that. On the internal side, on the containerized side, our devs are killing containers, spinning up new ones, just all day, every day. We've gone from sort of big pushes of major subversions to minor fix, committed to GitLab, image built, pushed to servers, and it's imperceptible to users. But that's in terms of internal services, because as I said, we're not doing the Anycasted SIP just yet.
All right, how about a big round of applause? Great questions, great answers.
Thank you.
Thank you very much, Simon.